For centuries, human industry relied on a simple observation that you can capture the physical weight of flowing water and use its movement to turn heavy machinery for grinding grain or cutting timber. We did the same on the open ocean, building massive cloth sails to catch the wind and physically push 1,000-ton wooden ships across the globe. This same logic applies to a modern ballistic collision. A small piece of lead fired from a barrel hits a solid surface, splintering it apart in a fraction of a second. The stream, the wind, and the bullet all share a single characteristic. Because they are in a state of continuous movement, they possess the ability to do work, the physical process of applying a force to move an object. In physics, we call this the energy of motion, or kinetic energy. Kinetic energy is the capacity an object has to do work by virtue of its velocity. This isn't just a description of movement, it is a measurable quantity. It tells us exactly how much an object can alter its physical environment before it is forced to stop. The challenge was turning this abstract idea of movement into a precise mathematical value. This formula defines that value. Kinetic energy equals 1/2 the object's mass times its velocity squared. Mass provides the baseline. If two objects travel at the exact same speed, the heavier object will always possess more kinetic energy and do more work upon impact. Crucially, kinetic energy is a scalar quantity, meaning it has magnitude but no direction. Whether an object travels north, south, or up, its total energy remains the same. Because direction doesn't matter, kinetic energy acts like a stored account of potential work, dependent solely on how massive the object is and how fast it's going. While mass is important, the second variable, the object's speed, is what makes this equation truly volatile. This graph plots velocity on the horizontal axis against energy on the vertical. Because the velocity in our formula is squared, the result is a steep exponential curve. Doubling your speed doesn't just double your kinetic energy, it quadruples it. This mathematical relationship makes speed the dominant factor in determining an object's capacity to cause physical change or destruction. A standard police ballistics demonstration provides a clear look at how this squared velocity rule works in the real world. Consider a 50-gram bullet fired at an initial speed of 200 meters per second toward a sheet of soft plywood 2 centimeters thick. Our formula tells us this bullet starts with exactly 1,000 joules of energy. A joule is the standard unit used to measure work and energy. As the bullet strikes the wood, it begins doing work, expending its stored energy to tear through 2 centimeters of solid fiber. The bullet emerges having lost 90% of its initial kinetic energy, retaining only 100 joules. If the bullet just lost 90% of its energy, it's intuitive to assume it also lost 90% of its speed, but the math tells a different story. When we solve for the final velocity using that remaining energy, we find the bullet is still moving at 63.2 meters per second. Even with a massive 90% drop in total energy, the actual velocity only dropped by about 68%. This proves that kinetic energy is not just a measure of raw speed, but a measure of an object's true capacity to do work.